Dr. Gollakota is a bread and butter missile man. Dr. Gollakota did his mechanical engineering from Andhra University in Voltaire and his MTech and PhD from IIT Bombay. He's then been with DRDL, and he has a very long biodata, but I like to just put it very simply. I think his entire stint at DRDL with the Integrated Missile Development Program has been really his work on the development of the BVR missile Astra. So I look forward to his talk, which should cover the IGMDB and particularly, I think, his love, the Astra missile. Please go ahead, sir.
Thank you very much, my esteemed colleague Ajay Raman. I am very happy that my ex-boss, ex-director General Sundaram is with us today. Actually, I have from a journalist to a scientist presentation now. I have basically prepared for the consumption of students and the young scientists. And I see that there are quite a few young people here. And I assume that the rest of the guys know more than I do in the field. So now I get on with the business of what we have been trying to do for the past, say, 3 decades plus, and where we are now. And I'll cover broadly what the DRDO has done in the field of missiles. What a missile is, most of you may be aware. Anything which is guided, we call it as a missile towards a target. Then you know there are different types of missiles. We have surface to air, surface to surface, air to air, air to surface, underwater launch, ship launched, and the class of missiles which DRDO has been making as part of IGMDP and later on the new programs. We have these kinds of missiles which you can see on the screen. Then you have the long range versions, the IRBMs, the ICBMs. Then you have, I spent a little more time on this Agni Missile, some of the strategic systems. The basic technologies and what is it you need to make, though all the missiles, they belong to the same family, each has its own very key signature in terms of technologies, materials, and avionics. If you look at Agni, you need a very large impulse, rocket motors, navigation, then very high-powered control systems, miniaturized, and most important, as he was mentioning earlier, he was talking about supersonic cruise, supersonic combustion, propulsion if you have. The challenge today is the question of the kind of materials you got to have which will sustain that kind of temperature for so long. And then you have auxiliary propulsion, thrust vectoring, and so on and so forth, reaction control systems, and then aerospace mechanisms, stage separation, and so on. I won't show a slide of this. You must have seen this several times earlier. Prithvi, of which General Sundaram himself has been a project director. It's based on a twin-engine liquid propulsion system, and then very accurate navigation and guidance, and the kind of warheads. And today's deployment scenario, if you look at more than the missile, what's important is the ground support system. Making a missile is not all that tough, but making a weapon system with the ground system or the platforms today is a real challenge. Similarly, the anti-tank missile, Nag. A little while ago, if you were here, around 12 o'clock, my colleague Varaprasad was talking about the Nag on the helicopter, which is called the Helena. Lightweight, tube launched, and you have a infrared imaging seeker head and fire and forget capabilities. This is totally indigenously made and has been successfully tested. Let me see if I can show you a video of this. And then coming to surface to air missiles. Mostly they are used against incoming fighter aircrafts they can be used against incoming missiles also. Broadly these days we call it as air defense, both exo-atmospheric as well as endo-atmospheric, which our SA himself has been pushing very hard. This is one of the success stories of the indigenous program. This we have gone way ahead. Then comes Akash, which is now going into production, large numbers, thousands. And here the trick is mobile formation, the weaponization, and the ground control systems, multi-target handling as a missile, and state-of-the-art countermeasures. Another important area is the ramjet propulsion. So that is where it has taken considerable time in integrating it's an actually integrated ram rocket. And then you have digital coded command guidance. You have a ground-based radar that steers the missile towards the target. And then of course automation. These are the things. Just one or two animations. I thought I'll show you one video. Firing in cell together. Then Trishul, we have spent a good deal of time and effort in this. We have learned a lot of things in this program. It's a so-called QQRM, quick reaction, high speed, high agility missile. And we have got a narrowband tracking system. And we have used a very special propellant in this and a dual thrust solid rocket motor. That is, you have the booster fired for some time and then you have the sustainer taking it along, and then fins are foldable. So this is also a very important system which we developed, though it could not enter the production. This is air-to-air missile scenario, animation. All it needs to make this kind of system. Has to make this missile, what all you need is you need a very high speed, high agility system. Then you have got a secure data link. The mother aircraft radar looks at the target. The information is passed on to the missile through a secure data link. Then you have dual mode guidance. That is, in the mid-course phase you have the inertial navigation. In the end phase you have got the terminal guidance using either a active radar today, of course, or using a dual mode radar. The name of the game today is all miniaturized systems. Even the electromechanical actuators which are used for moving the fins, they are all miniaturized. The wings are all low aspect ratio wings. So this is one of the flight trails, high speed movie camera we are showing you, just to show the kind of propulsion system which we have taken considerable time, because the Air Force asked for a smokeless propulsion system. Initially we had problems of combustion instability, so we had to do a lot of experiments, try with a lot of additives and other inert elements to make it totally smoke free. Then you have, in the category of air to surface missiles, you have against ground targets, against ships. These are the kind of systems we are trying to work. Then you have underwater and ship-launched missiles. Currently programs are on the DRDO. We also are making submarine-launched systems, both against strategic targets as well as ships, plus systems launched from the ship, like Dhanush, for example, against strategic as well as air targets. Now, of course, a lot has been said and a lot has been seen about Brahmos. I will not spend too much time, except that I will show one video for those who have not seen.
One now.
Supersonic cruise missile based on adapted technology using kerosene.
Trajectory normal.
It's a joint venture between India and Russia. It's a success story. Then you have the ship-launched version of same Prithvi variant. Here the technology is accurate transfer alignment and then autonomous and accurate navigation and integration with several of Indian naval ships. Now I dwell some time on what are the kind of generic technologies you need to make this kind of weapons. One is aerodynamics. Today's aerodynamics, if you look at tactical missiles, it is quite different from what you read in the books, especially when you go down to very small missiles with low diameter, low moment of inertia. It becomes a very highly complex aerodynamics, especially at high angles of attack. And the cross coupling between the pitch motion, the yaw motion, it's very difficult to figure out. You've got to do a lot of experimental work, CFD, flight testing, wind tunnel testing. And even then sometimes you find it extremely difficult to reconcile. And then material technologies, high specific strength. And then propulsion, of course you have got various propulsion systems today. We have ramjet, scramjet. And then different types of warhead. I will not spend too much time on, there are so many varieties of warhead. It is target specific. And then control and guidance. Control and guidance, the sensor, and the kind of accuracies you look for. Whether you want to make a missile or eventually want to make a hitile. A hitile which has almost zero miss distance, we call it hitile, so that you can reduce your warhead requirements and increase the effectiveness. And then the thermal batteries, the lithium ion batteries, the varieties of batteries which we develop for power supplies. So they are getting more and more miniaturized by the day. And the kind of energy density you get, V into I into T, it's amazingly large for its size and weight. And then of course actuators, they are also becoming smaller and smaller. We had earlier hydraulic, pneumatic, now you go down to electromechanical. Even these are becoming smaller by the day with new materials and powerful permanent magnets. And of course sensors, sensor technology, and the onboard computer. These things become obsolete very fast. In fact, when we started off with 8460 processor. Down the line, after 3 years, we had to change over to ADSP. Then after 1 or 2 years, somebody asked me, why don't you change over to PowerPC? Then when suggestion came, then I said, why PowerPC? I might as well go on to system on chip. That will be better. So the kind of, so we are trying to make the system which will not be obsolete, say 10 years, 15 years from now. That's our goal. These are all the generic technologies I have slightly modified from, as I said right in the beginning, from the Fleeman book. I have modified. There are so many iterations and so many sort of lessons we have learned. So we have modified all these basic elements, the technology elements. Then we have this is the kind of design cycle we go through. From the ASR, we arrive at the mission, then we establish the baseline, then we look at the aerodynamics, propulsion, weight, trajectory. Then after that you find that somewhere something is not okay, then you change over. In our case, for example, when we initially decised the actuators, when we put the actuators in the missile, we found that the length had to increase. The moment length had increased, to accommodate these actuators, we found that somewhere a local diameter had to be increased. Then we found the drag had increased, the propulsion was not adequate, the T minus D was not okay. So it goes into a kind of iterative cycle by the time you freeze your design. It takes considerable time. By the time you freeze that, some suddenly will say, why don't you change over from aluminum alloy to titanium? This is much better. The moment you change your titanium, you have some other difficulties, and the rocket motor remains in barraging steel, other elements become in some other material. So you have got stress corrosion and dissimilar materials. So all kinds of problems you get into. Then you have thermal problems, because these missiles go up to as high as Mach 5, Mach 5.5. So you have to take care of all these things. So suddenly down the line, say after 4 years or 5 years, you encounter new problems. So that's how the cycle time sometimes becomes longer. But in the end, if we decide that we do not do too much of experimentation, you get a product in a cycle time of something like 10 to 12 years. Then I come to weaponization. Then you've got ground batteries, you've got networking. Most challenging job, as far as my experience is, integration with platforms is as tough, if not tougher, than making the missile itself. Integrating with the trucks, ships, submarines, aircraft, and helicopters. Then you have issues at various speeds: subsonic, transonic, supersonic, hypersonics, exceeding Mach 5, 5.5, something like that. Then you have got problems associated with flow, internal flows, chemistry, external flows. And then what kind of shapes do you have to have? And today, for example, the slenderness ratio has touched almost 22, 23, even 24 also is not unheard of. Earlier days, the moment you exceeded something like 18 or 16, 18, people were worried. The interaction with control, between interaction with aerodynamics control, there was a flexibility. So today you've got powerful notch filters, autopilot design. So we do ground resonance test and take care of all these. Still there are limits to which you should not exceed. Then you have got very complicated approaches, design trade-offs. We take care of all these parameters which I'm showing on the screen. Then issues like stability and control. These two are by and large contradictory. For example, if you take a missile and if you want to make it very highly agile, you don't want the static margin to move far too much. As you all know, with changing Mach number, the center of pressure keeps traveling. And after the propulsion has burnt out, the CG remains practically same. So the kind of static margin travel we have creates a kind of stability problems. So the kind of static margin requirements you have at interception, the static margin requirements you need at the time of launch, taken from the safety of the aircraft, all these become a little contradictory. And at times it becomes very difficult to satisfy all the three. So we make trade-off studies and make sure that you decide which is of utmost importance. Is it important at the time of interception, or you want excessive stability and safety of the aircraft while you pay a price for agility? So these trade-off studies we make and take decisions. We keep the user in picture and then take these decisions. Then for aerodynamics also, it's a little complex. You at the time of design, you make some estimates, use tools like computational fluid dynamics, and then you would have internal testing. You always find some difference. And then when you start doing flight testing, and when you do the flight testing, probably you touch something like alphas exceeding 15 degrees or 20 degrees. And Mach numbers, something like interception Mach numbers, something like 1.4, 1.6, 1.8, or even bordering 2. For this, you don't have corresponding reliable data coming either from internal testing or estimates. And often you find that even CFD and the internals, as you all know, there's a lot of variance. Then we fall back on the parametric estimates which we do from the flight tests. And then over a period of time, something like you do 10 flight trials or 12 flight trials, then only have some reliable aerodynamic data, which is again used for the final design of your configuration. Again, when it comes to internal testing, you have got serious limitations. The type of test sections you can afford to have, the bigger the better, of course. The bigger the costlier also. Goes on like that, Mach numbers, interference. So finally we fall back on parametric estimates. You do limited internal testing, depend largely on your CFD, and take data from the parametric estimates, finally make a nonlinear estimating model. Then of course materials. In the fast changing scenario of materials, both in metals, composites, and even hybrid, you have got composites, you have got metals, you have got a combination of both, from structure considerations, strength considerations, from thermal considerations, and more important is availability. So all these considerations, and cost, of course. These are the kind of availability, storage, strength, cost, all taken together. You can always work out a table. We very judiciously choose the material, but spend a lot of time when it comes to testing to meet the requirements of airworthiness. That's a very tall order, and you spend a lot of time in testing. And in my program, we have spent a good deal of time in testing alone, all these kinds of steels, aluminum materials, composites, etc. Then comes to material choices. You have got factors of safety, you have got weight penalties, you have got the cost, availability, testing, aerodynamic heating, structure. So all these taken together, by the time you evolve something and start flight testing, the next day you get a new material option available to you. But then, if you look at your schedules, costs, somewhere you got to draw the line and say, well, look, Mark 1 or version 1, this is the kind of performance I can give. In the next version or in the next derivative, with better materials, we can give superior performance. Then while you do the design, it becomes a very complex affair if you get into again new materials, especially for insulation. Like if you have the rocket motor insulation internally, you have got ablative materials, you have got epoxy materials, you have got EPDM materials which are required for low temperature applications, and then various technology options, MEMS, composites, titanium alloys. So all these play a very vital role from the textbook level, design level, product level, flight testing, and finally weaponization and handing over to the user. Of course, these are all the propulsion options you consider at the beginning.
Another 5 minutes, please.
Okay. Then I'll skip some of these. These are kind of dual pulse rocket motor which we have built for our longer version of Astra, which can go up to 100 kilometers plus. It's a dual pulse rocket motor. You fire the first pulse, do the coasting for a while, and then fire the second pulse depending on the kind of scenario, engagement scenario you have. These are all the various kinds of warheads we study, and depending on the application we select one. This shows both charge type and fragment version. And of course control and guidance, you have got various options. I don't have the time to go through all these different types of power supplies which we have developed, thermal batteries, and then kind of actuators which I mentioned. This is a kind of electromechanical actuator which we have made for the program. And then different types of sensors, navigation, strap down, etc. And this is how the sensor growth has been over the period of time, starting from going up to fiber optic, quad zeros, seeker heads, active. Today you have RF, you have got dual mode, onboard computers. Then you make all the trade-offs. And then coming to checkout systems, you have got ground checkout, cockpit display, and then checkout systems for the tank well. and then various softwares, and then software verifications, modeling, simulation. And we do very exhaustive hardware loop simulation hills, and even the software is also thoroughly checked, IV and VE. And then onboard software, guidance, autopilot, the filter, especially for notching the flex effects, the estimators, the Kalman filters, the transfer element between the master INS and the missile INS, and then the integration techniques. Then comes the very time-consuming but absolutely essential part of the development, the environmental testing of all these schemes. Then still continues. Then design validation, technology development. To conclude, I will just show you the kind of technologies which we have developed for our beyond visual range, and then the captive flights which we have done on the Su-30. We have put 4 missiles, 4 Nag missiles, Su-30. There were a different number of sorties done, starting from low speeds to high speeds, and including steep dive down, to ensure that you have adequate aeromechanical compatibility between the missile. With this video, I conclude. There is a change aircraft following our Su-30, carrying the camera. All this was done by our AST pilots. Dive down is there. So we try to measure various corner points of the flight below the Su-30, the kind of vibration, the kind of stresses, and the temperatures, the missile, the launcher, they are experienced. You will see the steep dive down, going up to 1,450 kilometers per hour speed IAS. I'll skip all this, but I just wanted to show you one. Of course, there are all the various work centers, Similac, DRDL, Air Force, so on and so forth. Contemporary missiles, how they compare, AMRAAM, Mica, Astra, Derby, RVAE. These are the seekers. We are trying to develop a two-way data link between the missile and the aircraft. Different types of warhead which we have made for the Astra. And this is one chart which there was a national level committee during Dr. Athre's time, in which I was a core member. Dr. Amilmani was there, and then Mrs. Sitaram and others. We have evolved what is called a decision aid technique. The moment you make a project proposal, we analyze on the horizontal axis various technologies, on the vertical axis various subsystems, and look at the National Resource Index, and finally arrive at a figure called SRI, System Realizability Index. So in a scale of 0 to 10, if you are somewhere above 3.54, that means it has got a fair chance of success over a period of time. So with this, this doesn't stop the sanction of a project, but it will only guide people sitting in Delhi to tell you whether the project is a doable project or not a doable project. If you have any queries, you can talk to me on this email address. Thank you very much.
Thank you very much, Dr. Gollakota. In fact, the speaker has really done what he wanted to do. He complemented the morning's talk which was given by Dr. Shivdan Pillai. And between these two, they have covered what we have achieved in missiles and what are the aspects in a multidisciplinary missile system which we need to attack. And I think it will be a good learning process for all the youngsters who are available.
Thank you.
Thank you once again, Gollakota.
Thank you.